Swayam Prabha. Digital India. Educated India.
Welcome to 13th lecture in mechanics of materials. The last lecture we saw how to compute the change in length by original length for a line element oriented along a direction A. We saw that the expression for finding the change in length along a direction A is given by this expression where epsilon is the linearized strain, or it is 1/2 of gradient of u plus gradient of u transpose. Okay. So, if you take the strain tensor or the linearized strain tensor as 1/2 of the gradient of u plus gradient of u transpose, that tensor multiplied by the direction along which you want to find the change in length by original length and dotted with the same direction will give you the change in length by original length. Similarly, the change in angle between two line elements A and B is given by this expression in here, which is 2 times epsilon A dotted with B by sine of the angle between A and B, which is cos inverse of A dotted with B, okay, where A and B are unit vectors. Okay. Now, we will address a question on how to experimentally find the strain tensor. Okay. Now, we can't measure changes in angle directly using an instrument, and hence we have to infer the change in angle also by measuring changes in length along 3 different directions. Okay. For this you have to use what is called as a transformation of strain concept or the Mohr circle for strains to understand how to compute the strain, especially the strain component epsilon xy, because you can't measure the changes in angle directly. Okay. Towards that we will look at transformation of strains first. Strains. Okay. In the last class we saw that if you write strain as 1/2 gradient of u plus gradient of u transpose, it is a second order tensor, and we saw that how in the previous lectures how a second order tensor will transform when we looked at the stress tensor. So, since strain is also a second order tensor, it will transform similarly. So, if I write strain in one coordinate system and want to compute the strain tensor in the starred coordinate system, if I want to compute the strain tensor in the starred coordinate system, this will be what we saw before as q transpose epsilon q, okay, where qij we defined it as E j star dotted with ei. Okay. So, basically from that we saw the strain also will transform in a similar manner like the stress transforms. So, whatever equations we had for the plane stress transformations will hold for plane strain transformations also. In particular, these expressions that we got for sigma x star will hold for epsilon x star also, plus epsilon yy by 2 plus epsilon xx minus epsilon yy by 2 cos 2 theta plus epsilon xy sin of 2 theta, and epsilon y star would be epsilon xx plus epsilon yy by 2 minus xx minus epsilon yy by 2 cos of 2 theta minus epsilon xy sin of 2 theta, and epsilon x star y star would be given by epsilon xx minus epsilon yy by 2 with a negative sign sin of 2 theta plus epsilon xy cos of 2 theta. Okay. So, these are the Mohr circle equation that we obtained for the stress transformation, the same equations holds here. However, if I were to replace epsilon xy by the change in angle between x and y, which is related to epsilon xy as gamma xy was twice epsilon xy, like what we saw in the last class, then what happens is here it will become gamma xy by 2, and here this will be gamma xy by 2, and here also it will be gamma xy by 2. In that case, we saw that gamma xy, if you write in the strain in terms of gamma xy, it is no longer a second order tensor, and then the transformation rules differ by a 2 there. Okay. So, this is why it is important to treat the strain also as a second order tensor, so that you can use the same transformations like in the Mohr circle for stresses, you can use the same expressions for the Mohr circle of the strains. Okay. Now, let us see how electrical strain gauge functions. This is a schematic of electrical strain gauge. Okay. What it measures is the change in resistance. You know that the resistance is proportional to the length of the member. Okay. So, when the length changes, the resistance will change, and hence it will cause that change in resistance is what you measure as a change in the balance in the Wheatstone bridge network. Okay. So, basically now this is an example of a real electrical strain gauge. Okay. So, what you see there is essentially this small thing which is there, it is roughly 5 mm in gauge length. Okay. This length is essentially 5 mm, this red dimension is essentially 5 mm, which is the gauge length of this electrical strain gauge. Okay. Now, what you measure is the change in length along this direction, that is the strain direction, that is where the windings of the metallic wire are there. Okay, that is where the resistance wires are there, gauge resistance wires are there, and you measure how much change in length does this gauge resistance wires have. Okay. So, what you measure is this quantity epsilon A, that is epsilon A dotted with A is what you measure. Okay. Now, having measured this along 3 different directions, you can get the 3 components of the strain tensor. That is, what you do is you measure, you put 3 of these together, you measure 3, and if I take Ex and Ey as my coordinate system, and say this makes an angle theta 1 with the x, this makes an angle theta 2 with the x, and this forms an angle theta 3 with respect to the x axis. Then what I want to do is find this with respect to those 3 orientations. Okay. In other words, if I had to find epsilon x star 1, which is for this theta 1 direction, it will be epsilon xx cos square theta 1 plus epsilon yy sin square theta 1 plus epsilon xy sin 2 theta 1. What I have done is the previous expression I have combined again, the previous expression I have combined 1 plus cos 2 theta by 2 as cos square theta 1. Okay. I combine 1 minus cos 2 theta by 2 as sin square theta 1. Okay. That is what I have done here, because that will yield me a equation which is convenient to handle. Okay. So, this is epsilon xx star 1, which is nothing but the strain measured along this is epsilon xx star 1. Then similarly let us say this is epsilon 1, epsilon 2 is the strain measured along this direction, this is epsilon xx star 2, it is epsilon 2, that will be epsilon xx cos square theta 2 plus epsilon yy sin square theta 2 plus epsilon xy sin 2 theta 2. Okay. Similarly, for the third direction you will have epsilon 3 as epsilon xx cos square theta 3 plus epsilon yy sin square theta 3 plus epsilon xy sin 2 theta 3. Okay. Now, this is 3 equations in terms of 3 unknowns, this is epsilon xx, yy and epsilon xy, which you can solve to get epsilon 2, epsilon 3 is equal to, I have cos square theta 1 sin square theta 1 sin 2 theta 1 cos square theta 2 sin square theta 2 sin 2 theta 2 cos square theta 3 sin square theta 3 sin 2 theta 3 times epsilon xx, epsilon yy, epsilon xy. Here I do not know this is known, this is unknown. I invert this matrix and I can find the unknowns in terms of the known vector. Okay. So, this is how you measure epsilon xy. Okay. There are different strained Rosettes, this is called as a strained Rosette, it is called as strain Rosette. Okay. There are different kinds of strained Rosettes, one which makes an angle 45 degrees, where this angle is 45 degrees and this angle is also 45 degrees. This is called as 45 degree strain Rosette. Okay. Similarly, there is a 60 angle strain Rosette wherein now the angle between the strain gauges is 60 degrees. Now, this is 60 degrees and this also 60 degrees. Okay. This is called as a 60 degree strain Rosette. Typically what will happen is in real life this branch would be drawn here and it will be like a equilateral triangle. This branch would be translated here and it will be like an equilateral triangle. Okay. So, that is how a real Rosette will look like, and this Rosette is supposed to measure the strain at the CG of this triangle, equilateral triangle. So, the strain is at this point, the measurement point is that point. Okay. So, what you do is you measure changes in length and from the changes in length you measure the changes in angle, and if you are going to follow this procedure to compute the strain, you will use what is called as a strained Rosette to compute the in plane strain components. Okay.